Hi, everyone. This is Circular Motion Part 3. Here we're going to talk about uh, tangential acceleration and radial acceleration. Because there are two components to these acceleration vectors that we haven't talked about before. So we're going to dive into what the acceleration is doing to cause circular motion. So let's look at this right here, combination of tangential and radial acceleration. Compare radial and tangential acceleration. Which acceleration are they describing? So let's just look at this image right here. We have the acceleration vector. First, let's also note that this is not just a normal circular path. You can see that this is snaking along. It is not just a normal circle, right? So if we zoom in here, the acceleration is not purely centripetal, which means radial. It's not purely centripetal acceleration. That angle, the acceleration is coming off at an angle, right? You have this uh, acceleration right there. It's not purely radial. So, uh, what it wants to know is which acceleration are they describing? So, if we have this acceleration here, radial, okay? Radial acceleration is it's talking about the acceleration towards the center, right? So here, radial, okay, is toward the center. Or you could also think um, along the radius. Okay, and that's what, remember we talked about this, that's what causes the change in direction in that velocity vector. Because that's the only change we have here. The velocity shouldn't, velocity usually is not changing a whole lot in uniform circular motion, or at least the magnitude, the speed is not changing a lot, but the direction is obviously changing to go in a circle. Now, if we look at the tangential acceleration, tangential acceleration is really going to cause the velocity to change its speed, right? So this is acceleration that is 90 degrees of that radius. And this can lead to speed change instead of direction change. Now, uh, those are the two accelerations that we have here to discuss. Now, we could put this in equation form. What equations can we use that are analogous to using I and j components to analyze a system? So this is kind of, tangential can be your x, radial can be your y. We can use our knowledge of vector components to knock this out. So first, we've got a triangle system up here, right? If we take this right here, right? We've got our acceleration vector here. We have our radial vector here. And then we have our tangential vector here. Now, if we can move these away from that image so that we can better analyze them, we can see that this will give us a circle. I'm sorry, not a circle. This will give us a triangle like we are used to using with a vector, right? You can analyze it in the I and j to give you the total vector. So this is not an unusual thing that we're trying to do here. So if we want to describe a triangle, one thing we can say is that the total acceleration is equal to the square root of radial acceleration squared plus tangential acceleration squared, right? That's one way to do it. You could also look at the trig of the scenario, right? You can, depending on the angle that you're using, right? If we zoom in over here, we can use this angle theta. We could use this angle phi. Phi is just another Greek letter to describe an angle. So What most importantly you can do is you can use theta equals the tangent inverse of some x, right? Where that x goes is going to depend on the triangle that you're drawing, right? If I drew that a little differently, or we looked at theta instead of phi, or phi instead of theta. Hello? Sorry about that. So we can find the angle theta if we look at the tangent inverse of some quantities, right? So this is usually going to be, what is it, TOA? So that's opposite over adjacent. So honestly, let's just use opposite over adjacent, because that could mean, depending on where you put your angle, that could be the tangent inverse of your radial over your tangential, or that could also be the tangential over the radial. There's really no way to know until we narrow down what angle we're using. But that is a technique that is definitely useful when we are using radial and tangential, right? So those are two equations that we can put both of those together, centripetal and tangential. Remember, centripetal and radial go together. Right? So two equations that we've got, the Pythagorean theorem and tangent, relate both of those together. All right, next slide. Radial and tangential acceleration in one problem. So the figure shows the total acceleration of a particle moving clockwise in a circle of radius 2.5 meters. For the instant shown, we want to find A, the radial acceleration, B, tangential acceleration, C, the tangential velocity, and D, which acceleration leads to tangential velocity change. So start with letter A, radial acceleration. So what are our givens? Let's see, we have a radius of 2.5 meters. The acceleration vector is 15 meters per second squared, and we have an angle theta of 30 degrees. Now, first, letter A, we want to know the radial acceleration, which is centripetal acceleration. So what we can do for this, we don't have velocity, right? We don't even have omega, but we do have a triangle. So let's draw this triangle real quick. Let's see, that was the radius. The hypotenuse comes off there at 30 degrees. And bingo bango, there we have our triangle. That's a right angle. Let's get the radial as the long end. Tangential will be, right? So this will be AR, this will be AT. Right? Because we can see here that this is along the radius, and then this would be along the tangent. So that's how we're able to determine those. And that can be tricky sometimes. Make sure that you get your triangle correct. So if we want to find AR, we would take A. Let's see, we want to use adjacent, which would be cosine, right? So we'd A cosine 30 degrees, because cosine of 30 degrees would be adjacent over hypotenuse, which would be AR over A. We want to solve for AR. So we have 15 cosine 30. Let's see what that comes to. 15 cosine 30. That would be 12.99. We'll call that 13. And that is in meters per second squared. Okay. So that is our radial acceleration. Now let's find part B. We want tangential acceleration, AT. Now, we already have the triangle drawn. This should be relatively simple. That is opposite of that angle, so we could use sine of 30 equals opposite over hypotenuse. So this could lead to a sine 30. I keep putting an m in there. Sine 30. Get 15 sine 30. What is 15 sine 30? 7.5. Sine 30 is 1/2, isn't it? There we go. So we have our acceleration in the radial direction and our acceleration in the tangent direction. And it looks like radial, is pulling stronger, but we do still have tangential acceleration. Now let's find the tangential velocity. So we do have an equation that uses that velocity, right? That would be centripetal acceleration is v squared divided by the radius. But notice that we have to use centripetal acceleration. That's the equation that we've been using. So if we use that, v is the square root of ac times r. And ac is up here. Radial acceleration is what we're going to use, centripetal. We take 13 times the radius, which is 2.5, square root 32.5 to get 5.7. 5.7 meters per second at that instant. Now, with all of these acceleration vectors, you can bet that that is probably going to change over the course of this acceleration, right? So over a couple seconds, that's probably not 5.7 anymore, but at that instant, it is. Now, if we look at part D, okay, that asks which acceleration leads to tangential velocity change. So this is kind of confusing, but radial acceleration is what we will use to find tangential velocity, right? So radial acceleration is what causes the direction change, and it's what usually is the leading factor in uniform circular motion. It is also the one that we have all of the equations for. So that is going to be the one that will lead you to tangential velocity change. So that can be confusing. So remember that radial acceleration, which is synonymous to centripetal acceleration, that is going to be the main acceleration that we will use doing these problems. Now, tangential acceleration can come up, but radial acceleration is what drives the circular motion. Right? All right, one last problem for this video. Hang on, kid. A kid who weighs 200 newtons is sitting on the rim of a merry-go-round that is 3 meters in diameter and spins at 0.5 revolutions per second. About how many pounds does the kid weigh? 200 newtons. Newtons to pounds. That is, whoops. Okay, let's go to kylesconverter.com. 200 newtons. That is, oh, this is not a big child. That is only 45 pounds. So this is a relatively small child, as I guess that makes sense given the picture that we have there. 45-pound child. Okay? So calculate the radial acceleration. Let's get our givens. Right. So we have the force of gravity on this child is 200 newtons. The merry-go-round has a diameter of 1.5, so that is a radius, diameter of 3, radius of 1.5 meters. And it's got an omega spinning at half a revolution per second. Okay. Now, we want to find the radial acceleration. So if we have, which is again centripetal acceleration like we have in our equations, that would be omega squared r. We have omega, we have r, let's plug it in. 0.5 squared times 1.5. What's a quarter of 1.5? That's like 0.375. Yeah, 0.375 meters per second squared. Is that meters per? Yep, meters per second squared. All right. So we have our radial acceleration of 0.375. Now, can we calculate the tangential acceleration? Well, let's see. Our equations that we have for tangential acceleration are the Pythagorean theorem, and then we have tangent theta. But that doesn't help us here. It doesn't look like we will be able to calculate tangential acceleration. We just don't have enough information, which is not uncommon. It's sometimes you just can't calculate tangential acceleration because, like I said, centripetal gets all of the fame and glory, radial and centripetal. So you won't be able to calculate tangential all the time. Now let's calculate the amount of force required to stay on the moving toy. Let's see, how would we do that? The force required to stay on the moving toy. Well, we did talk about centripetal force, right? Centripetal force is MAC. We have AC. We could find the kid's mass, right? Force of gravity is 200 newtons, which would be the mass of the kid times 9.81 meters per second squared. So if we take 200 divided by 9.81, that should give us the mass. Let's do that. We get 20.39, and that is in kilograms. So if we take 20.39 kilograms times 0.375 for the acceleration, we have 7.65 newtons. That is the force that you would need to balance to stay on, right? So the centripetal force is the force that is pushing you. It's kind of interesting with centripetal force, right? So we know that there is the acceleration that is causing you to spin in that circle. The force that is pushing you in that circle is the one that you would need to use to stay moving in that circle, right? This is the force required to maintain that centripetal acceleration, which is 7.65 newtons. All right, that is our last video for circular motion. From here on out, we've got a take-home test, and then you guys will take the test later on, and then we will move on to chapter 5.